Yesterday we defined energy as the ability to do work. And now when we say that, the ability to do work, it may be actually doing work right now, or it may be just kind of waiting to do work sometime in the future. If it's doing work right now, then that means we got something that's moving. And if something's moving, it's got what we call kinetic energy, the energy of motion, the energy of something that's doing something right now versus potential energy, which we define as stored energy, but really amounts to the energy of something that isn't doing something right now, but has the potential to do something down the road. Kinetic energy, when something's doing something, or energy of motion. Potential energy, when something is waiting to do something down the road, or stored energy. Now, we gave you an equation yesterday for kinetic energy. It looked like this. EK is equal to 1/2 mv squared. EK stands for kinetic energy, of course. What are the units for kinetic energy? Joules. In fact, the units for any kind of energy, including kinetic or potential energy, are joules. Is kinetic energy a vector or is it a scalar? It's a scalar. You might remember that there's no direction associated with it, or if you don't remember it, just check your data sheet, check the equation. If you don't see the little half arrow over top of it, it's got to be a scalar. What about M? What does that stand for? Mass. Don't say weight, right? Weight is the force of gravity acting on an object. This is not force of gravity. This is the mass, the number that's the same anywhere in the universe. And what units do we have to use for mass in this equation? Got to be kilograms, right? V stands for speed. Good. And the speed is a scalar, of course, and it's going to be measured in meters per second. How do you convert kilometers per hour to meters per second? Times it by 1,000 to get meters per hour, and then divide by 3,600 to get the hours to seconds. So times it by 1,000, divide by 3,600. Now, potential energy, we have some subcategories of potential energy that we talked about yesterday. We referred to a number of them, but two in particular. The first kind that we really focused on yesterday was called gravitational potential energy. In the equation that represented gravitational potential energy, that's the potential energy due to the height of an object above something is equal to mgh. EP stands for potential energy. Units are vector or scalar? Scalar, good. M stands for mass. Units are kilograms. Is mass a vector or a scalar? Good. G is the acceleration, not the force, but the acceleration of gravity. We say that G is usually going to be 9.81 meters per second squared. We make it a positive because energy is a scalar, right? We want a positive number for EP. Can you give me a situation where G would not be 9.81 in this equation, though? On the moon, it would be about 1.6, or on some other planet, it would be something other than 9.81. On the surface of the Earth, even though it does vary a little bit depending upon how far above or below sea level you are, we're going to say that it's 9.81. Top of Mount Everest, it might be 9.75-ish. In New Orleans, which is below sea level, it's going to be maybe 9.83, 9.82, something like that. We'll say 9.81 anywhere on the Earth, and then some other number if we're somewhere else other than on the surface of the Earth. H stands for what? Height. The units are going to be meters. Make sure that you measure your height relative to something. You can choose that frame of reference, right? The height of this board marker right now relative to the ground is about 1.5 meters, about 1.5 meters. The height of this board marker relative to my hand is what? 0. So we would say the potential energy relative to the floor is something, mgh, h being 1.5. The potential energy of it relative to my hand is 0. How much potential does it have to fall to the ground? Something. How much potential does it have to fall to my hand? None, because it's in my hand. You can define the height relative to whatever you want. Just make sure that you specify that and make sure that you're consistent through the question. So if you're defining it relative to your hand, that's fine. Do it that way through the whole question. Relative to the floor, that's fine. Just make sure that you do it that way through the whole question. Now, the other kind of potential energy that we dealt with yesterday was elastic or spring potential energy. We'll focus on that just a little bit in this unit, focus on it a lot more in our last unit on what we call simple harmonic motion. The essence of it, though, yesterday, we saw was that when we have a spring or an elastic that's stretched or compressed, or something like a spring or elastic that's stretched or compressed, maybe the bumpers on a bumper car, okay, that compress when two cars hit, right? It stores a certain kind of energy that we call elastic potential energy. The energy due to a stretched or compressed spring or elastic. The equation that described that was 1/2 kx squared. What did K stand for? No. What did K stand for? The elastic constant or the spring constant. It was measured in newtons per meter, and the higher the value of that value of K, the stiffer the spring was, and the more potential energy that it could possibly store. X was the displacement. And that displacement, we distinguish between that displacement and the displacement that we've used up until yesterday. That displacement that we used up until yesterday was delta D with the arrow over top of it. And that referred to how far something has moved, its change in position. This displacement refers to what? Yeah, how much it's stretched or how much it's compressed. And what are we going to measure that in? Meters. Good. Always going to measure that in meters. Good? All right. We had some questions for homework yesterday on kinetic energy. I want to take a look at those 3 questions now on page 303. Any issues with any of those that we need to go over here right now? Questions 1, 2, or 3? Number 3? Yeah? Anybody for 2? Yes? We got 2 and 3. All right. Number 2 says a car traveling at 80 kilometers per hour on a highway has kinetic energy of 420,000 joules. What's the mass of the car? Drop the blue pen, picking up the red pen. How come I'm doing that? What do I want to highlight? Something important, sure. Kilometers per hour. Draw attention to that because we don't want to forget to convert that to meters per second. This is a relatively straightforward kinetic energy problem, although I do have to do some algebra and rearrange, right? And convert, obviously, from kilometers per hour to meters per second. We got a speed of 80. Let's convert that right now. 80 times 1,000 gives me meters, and then divide by 3,600 gives me meters per second. And I think when I do that, it gives me 22.2 repeating meters per second. The kinetic energy of this car is 4.2 times 10 to the 5 joules. And we're looking for the mass here. So my equation that describes this, of course, is EK is equal to 1/2 mv squared. I want to rearrange this to solve for mass here. How do you want to get rid of this half in the v squared? Can we take over 1/2 and the speed squared together? Sure we can. They're both attached. We can take them both over together. We say v is equal to EK over 1/2 of m. That make sense? That's correct. Sorry, 1/2 of, that's not right. M is equal to EK over 1/2 of v squared, right? Is that right? That's better, right? Now there is another way to do this, a slightly different way to do this. You could take over the v squared. Sorry, what am I doing here? You could take over the v squared, but you'd be stuck with a half there, right? Another way to take over that half is to multiply by 2. You divide by half, multiply by 2, and you end up with m is equal to 2 EK over v squared. I sometimes do it like this just because it's a little bit tidier. It's no more correct, though, just a little bit neater. Instead of dividing by a half, right, dividing by this number, I'm multiplying by the number that it's all divided by, which is the 2. We'll stick with this since it's what you told me this morning here. My value of EK is 420,000 joules. And what do we got here? Let's put 4.2 times 10 to the 5 in our calculator. Divide that by, use some brackets. 0.5 times 22.22 squared. If you don't use brackets there around this whole thing, then your calculator is going to assume that you're dividing 4.2 by a half and then multiplying the whole thing by 22.22 squared, which is not what you want to do. Do the math there, works out to be 1.7 times 10 to the 3. Is that a reasonable mass for the mass of a car? 1,700 kilograms? Sure it is. It's right in that ballpark that we would expect to get. Good. What was the issue with that one? Was it the rearranging? Was it the speed? Converting it to meters per second? Forgetting to do that maybe? Okay. Yep. Sure. Yeah. Yeah. No, they wouldn't have needed to do that for that first one. 1.91 times 10 to the 2 would be the same thing as 191. And there's no reason why you'd have to convert that to scientific notation unless they specifically ask that. All right. 3. A skateboarder with a mass of 65 kilograms increases his speed from 1.75 to 4.20 as he rolls down a ramp. What's the increase in his kinetic energy? Let's think about what's going on here. Okay, we're looking for increase in kinetic energy. That's a change, right? What's a symbol for change? Delta. Good. Triangle, delta. The increase in kinetic energy, therefore, would be delta EK. Now, delta anything is anything final minus anything initial, right? Delta E will be E final minus E initial. Or delta EP will be EP final minus EP initial. Let's write down some givens now that we kind of figured out what's going on here. We know that my mass is 65 kilograms. We know that VI is 1.75 meters per second, and VF is 4.20 meters per second. And of course, we're looking for delta E. Should be delta EK, I guess, shouldn't it? All right, EK final is 1/2 MVF squared minus EK initial, 1/2 MV initial squared. 1/2 of 65 times 4.2 squared. Subtract 1/2 of 65 times 1.75 squared. Do the math there, and it works out to be 474 joules. Did anybody try this? Did anybody try saying, oh, look, delta EK is going to be the same thing as saying 1/2 M times delta V squared? Subtract the V's and then square it? It gives you the wrong answer, right? Does anybody know why it gives you the wrong answer? Why can't you just subtract the speeds and then square the difference in speed?
Because when you square it, it's different than just
Yeah, that's exactly it, because you've squared it, right? If it was a linear relationship between EK and V, you could have gotten away with that. If we were increasing the mass, not the speed, that would have worked. But since you're increasing the speed and it's not a linear relationship with EK, then that's not going to work. Listen, why don't you just do it this way, even if it is the mass that you're changing, okay, even though it might take you a tiny bit longer, you're guaranteed of it working. Right? Find the final, find the initial, subtract the two, and there you go. I want to spend a couple of minutes now, just a couple of minutes, talking a little bit more about gravitational potential energy. It's the energy stored, we said, due to an object's height above the ground or above something, right? We can define it relative to the ground or whatever we want. Something has the potential. It's not doing something right now, but it has the potential, the ability to fall, the ability to be converted to kinetic energy if it has a height. So we're going to say it's the energy stored in an object due to its height above the ground. And remember that it's always measured relative to something else. The board marker is measured either relative to the floor or relative to my hand. Doesn't matter which, as long as we specify and as long as we're consistent. Also remember that, of course, the larger the height, the more potential it has to fall to the ground. So we would say the more potential energy that it stores. The equation that describes gravitational potential energy, we've already written this down, but I'll write it down again here. EP is equal to mgh, where m is the mass, measured in kilograms. G is, I'm going to write down 9.81 meters per second squared, but remember that number can be different if we're somewhere else. And h, not delta h, not the change in height, but just h, is equal to the height of the object relative to whatever, and the units are going to be meters. E is potential energy, and the units are going to be joules. All right, let's have a look at a problem here. Here it is on page 298. It says, in this example, 6.14 shows a toy car track set up on a tabletop. We want to find the potential energy, the gravitational potential energy, relative to the floor. Could we find it relative to the tabletop? Sure we could. Could we find it relative to the top of the track? Sure we could. The only difference would be the height that we use in that calculation. If we want to find it relative to the floor, then we need to use the height of this toy car relative to the floor. Let's do A now. The potential energy of it at the top relative to the floor is simply going to be mg times h. M will be 0.0250 kilograms times 9.81 meters per second squared times the height of what height are we going to use? 2.15, 0.95, or the difference between the two of them? 2.15. Okay, that's the height of this car relative to the floor, so let's use that. We get 0.522729 joules. Good. We're going to find the change in potential energy of the car when it arrives to the bottom of the hill. We're going to say delta EP because change is delta. MGH final minus MGH initial. We've already found that, right? MGH initial is 0.52729. That's what it started with at the top of this hill. So all we have to do really is find the final. We're going to say it's 0.0250 times 9.81 times the height at the end of this problem. What's my height at the end of this problem, HF? 0.950 relative to the floor. Again, we can define the height relative to whatever we want, but we have to be consistent through this question. We can't just change it midway through the question. They actually give us our frame of reference here. They say relative to the floor, so you got to do that and stick with it. But we know what this MGHI is already. We don't need to find it again. 0.52729. And we'll do that. I think we get 0.294. Do the subtraction. Oh, yeah, you're right. Actually, it should be negative. Good point. Negative 0.294 joules. This actually should be rounded to 0.528, right? Why should it be negative 0.294? Did we say energy is a scalar? Doesn't negative mean down? What's the potential energy here? 0.294 joules downwards or left? Jackson, what does the negative mean? Yeah, all it means is a loss of potential energy. You're not going to get a negative E. You're going to get a negative delta E. And that negative doesn't have anything to do with direction. That negative has everything to do with how much it's changed by. If it's a positive value, it's gained energy. If it's a negative value, it's lost energy. If this toy car loses 0.294 joules of potential energy as it goes down this ramp, how much kinetic energy do you think that it would gain? Because it speeds up, right? Clearly it speeds up. It's going to lose potential. It's going to gain kinetic energy. It gains what it's lost, yeah. If it's lost 0.294 joules of potential energy, it would gain 0.294 joules of kinetic energy. Yes. In the middle of the track, then we would have an equal amount of kinetic and potential energy. I shouldn't say that. If you're defining your ground level as the tabletop, then halfway down the ramp, then the initial the kinetic energy and the potential energy would be the same. Okay? Good? All right, let's take a look at these three questions, please, on page 298 that relate to what we've just been doing. Let's take a look at number 2. It says a roller coaster trolley begins its journey 5.25 meters above the ground. Maybe we should draw this out, do you think? Begins its journey 5.25 meters above the ground. So here it is, like right here. And it tows it to the top of the first hill. There's the first hill, and it gains 4.2 times 10 to the 5 joules of gravitational potential energy. What variable do I have given to me there, that 4.2 times 10 to the 5? What is it? No, 4.2 times 10 to the 5 isn't initial height. It's delta what? Yeah, it's delta EP. Not EP. Okay, that's what you got to be careful of there. It's not EP, it's delta EP. It's the change. So as it gains or if it loses, then that's going to be the change in potential energy here. The mass of it is 875 kilograms. And we want to find the final height right here. So how are we going to go about doing that? Well, we know that EP is equal to mgh, but we know that delta EP is equal to final minus initial. So we're going to say delta EP is equal to mgh final minus mgh initial. We know what delta EP is. It's 4.20 times 10 to the 5. By the way, if it was going down the hill, then what would we make EP? It would have lost 4.2, so we would make it negative, right? Mass is 85 kilograms, 875, I should say, times 9.81 times the final height, which is what we're actually looking for, minus 875 times 9.81 times the initial height, which is 5.25. So what you got to do is get this number and then take it over to the other side by what? If it's negative 875 times 9.81 times 5.25, take it to the other side by adding. And then divide by brackets 875 times 9.81. That's going to give me my final height there. When you do that, you should get 54.2 meters. Here's what some people in the other class did, and I saw at least one or two people in this class do the same thing. It's a really, really easy mistake to make. This is not correct. So whenever I'm writing down in green here, don't write this down because it's wrong. Look, EP is equal to mgh, but EP is not 4.20 times 10 to the 5, although some people did that. We know what H is, what M is, 875. We know what G is, 9.81. We solve for HF. That's wrong, right? Because my final potential energy is not 4.2. My gain in potential energy is 4.2. So we can't just arbitrarily set that to equal to E. It's not E. It's delta E. So don't do that. Okay, be conscious when you're reading a question of what you actually have, specifically E or delta E. If you did that, then you're going to end up with an energy, or sorry, a height, I think, of something like 49. Yeah. Yeah. Okay, so that can be legitimate if you recognize that you have to add the 5 to it. Yeah. Hold on. What you're doing there is saying, is in a sense, defining the initial point as 0, saying, oh, okay, the initial potential energy would be 0, the final would be 4.2, and that gives me a final height of 49 meters. But then you got to say, oh, wait a second, though. There was an initial height of 5.25 meters, so I got to add that to my new final height. That works as long as you understand what's going on there. Okay, now I want to do question number 3. This one I think is the trickiest of the 3 questions. Some of you guys got this. That's good. If you did, or if you didn't, then let's focus up here for just a moment, okay? This one says a winch pulls a 250 kilogram block up a 20 meter long incline that's tilted at an angle of 35 degrees to the horizontal. What's the change in potential energy that the block undergoes? So here's my incline, 35 degrees. I'm pulling this thing up a 20 meter long incline like this. I want to find its change in gravitational potential energy. We know that change in potential energy is equal to final minus initial. So we're going to say it's mgh F minus mgh I. We know what M is. It's 250. We know what G is. HI. You know what? We can define HI wherever we want. Probably makes sense to do it at the bottom of the hill, as long as we're consistent through the problem. What's HF going to be? 20? We can't just arbitrarily write down a number for HF just because it's the only number we have. We need the final height here. We don't have the final height. How might we find it? Yeah. Say sine 35 degrees. This is not an inclined plane problem, but we do have to deal with that angle. Sine 35 degrees is equal to the height over 20 meters. That's going to be the opposite side of the hypotenuse. So h ends up being equal to 20 sine 35. And when we get that number, we're going to plug it in down here for hf. So we have m, we have g, and now we have hf. We just found it, right? We have m, we have g, we have hi. Hi is 0. mg times 0 is 0. Do the math there. The change in potential energy ends up being equal to the final potential because we defined the initial potential as 0. We could have defined down here as 0, but it makes sense to define this as 0 as long as we're consistent through the problem.